So let's actually do an explicit example using actual numbers. Here's a graph, and here's some data points. The x-axis is the horizontal axis, and the y-axis is the vertical one. And let's just use a unit grid so that the distance between any two of these grid lines has length 1. So the data that we're given, according to this plot, is we have our data vector, and we want to try to fit to a line of the form y equals mx plus b. So let's write down our matrix A. And our matrix A, remember, consists of all of the x's, if we write it in this form, and 1's all along the right column. So how many data points do we have? So what's D? 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. So you should have 7 entries in this column, in the columns of A. And let's go in order from left to right, filling in all of these entries. The order that you go in doesn't really matter as long as you're consistent with the corresponding values of y that you use. So in this case, the first value of x is at x equals -4, -3, -1, 0, 1, 3, 4. I've chosen it to be somewhat symmetric just for convenience of the computation. So it's -4, -3, -1, 0, and the x values, positive x values, are 1, 3, and 4. So this is the matrix A. And the vector y is the corresponding values of y. So for x equals -4, the value of y is at -1. Again, there are D entries here as well. The next one is 0. Then it's 1, 0, 1. And the last two are 2 and 4. So this is all of the information that we need. And if we compute A transpose A, what do we get? So I won't write out A transpose, just take the transpose of this. Then we know that we're taking the dot product of this vector with itself to get the top left entry here. So what's the dot product of this with itself? It's 4 squared times 2, so it's 16 times 2, which is 32. 9 plus 9, which is 18, so 32 plus 18, which is 50, plus 2. So it's 52 on the top left. The dot product of this with this is 0 because all the negatives cancel out all of the positive entries. Again, I chose that specifically so that this happens, so that computing the inverse is much easier. And we can immediately solve this system. Now, A transpose acting on y, oh, sorry, the bottom entry is just D itself, and D is 7. Now, A transpose y is this times this plus, so -4 times -1 plus -3 times 0 plus -1 times 1, and so on. So -4 with -1 gives you 4. That with 0 doesn't change anything, so we still have 4. Then that's -1 from 4, so that gives us 3 left over. This one brings it back up to 4. Then this 6 brings it up to 10. And this is 16, so we get 26 in the first entry. Maybe you have faster ways of doing this, I don't know. So then A transpose, if we take the second row here of A transpose, which is this column of 1's, and we dot it with this, these cancel, these add, so we get 7. Now solving this system is pretty straightforward. Right, this is 52,007. In one side, 26,7. We just have to divide everything by 50, the first row by 52, the second row by 7, and we immediately arrive at the vector MB. Our vector of unknowns is 1/2 and 1. So this tells us that the best fit approximation that minimizes the vertical distance squared between that line and all of these data points has slope 1/2 and y-intercept 1. So the line that we want to fit this to is 1/2 x plus 1. And if we try to sketch what that graph looks like, we know that it goes through 1. So let's include that point here. And it has slope 1/2. So when it gets to this, when it moves 2 units over, it moves 1 unit up. So here's the next data point. We connect these two with a straight line. And moving over 2 units to the right, 1 unit up. We connect that with a straight line. And we keep doing this. I mean, this is how I draw if I don't have a ruler or anything on hand. I would try to draw something like this. So this straight line here, if you notice, it happens to actually go through one of the data points. That might not happen. But as you can see, it doesn't go through most of them. But it's a pretty reasonable approximation to this data set. So this is how you would actually solve a least squares problem, specifically in the context of fitting data to a linear curve, or rather an affine curve to be technically correct. And this is how you would do it in such an example.